Lorentz force. Now we will consider what happens if this charged particle is inside an electric field and a magnetic field. So if this charged particle, which has charge Q, has a velocity v, subject to an electric field E and magnetic field B, it will experience a force which is the sum of the electric force and magnetic force. Electric force is Q times the electric field, and magnetic force is QV cross B. So this total force is called the Lorentz force. So it's QE plus QV cross with B. Now we will consider some applications. The first application is the velocity selector. You can see that this particle, this charged particle, is in between two plates of uniform charge density, plus sigma and minus sigma. So there is a uniform electric field E here, which points from positive charges towards negative charges. There is a uniform magnetic field which is into the page, so it has these crosses you can see here, and therefore this charged particle will feel an electric force Fe. It will be attracted towards the negatively charged side, repelled by the positively charged side, so electric force will point to the right. The magnetic force depends on the direction of its velocity. If it's coming from a source going through this collimating slit, giving us a beam of these charged particles, this charged particle has a velocity v, which is basically perpendicular to the electric field. You can see, using the right hand rule, if our four fingers point in the direction of the velocity, we curled our fingers towards the magnetic field into the page, the thumb points to the left. So this is a positively charged particle, so it will be to the left. So you can see that we have these two forces, magnetic and electric forces, acting in opposite direction. So if there is going to be no deflection of this charge, what will happen here for the linear motion of this particle in between the plates is that these two forces should balance each other. So QE, the electric force, must be equal to QVB, the magnetic force, and the charges will cancel, and we will see that the speed of the particle must be equal to the magnitude of the electric field divided by the magnitude of the magnetic field. So what does this tell us? Only those particles with this speed can pass undeflected through mutually perpendicular B and E fields. So basically, if we have a beam of particles here which have different velocity directions, only those with the speed E over B will go through this setup undeflected and reach the other side. This is called a velocity selector. So out of the beam of particles, only those particles with a velocity vector that is perpendicular to the magnetic field and electric field with a magnitude E over B, the speed E over B, will go undeflected in between the plates and reach to the other side. So those particles will be selected. Okay, so we've talked about the Lorentz force, which tells us the net force acting on a charged particle inside an electric field and magnetic field. If the charge is moving with velocity v, QV cross B is the magnetic force, QE is the electric force, so the sum is the Lorentz force. And in the case of the velocity selector application, if we have a uniform electric field and uniform magnetic field, we can see that the electric and magnetic forces will balance each other, QE equals QVB, when the speed is E over B. So only those particles with a speed E over B will go undeflected through this setup and it will reach the other side.